So the second part of locus questions. Okay, so they ask us to find the locus. So if omega is equal to some function of z, so we're basically talking about functions here. Find the locus, and they'll ask us to find the locus of either the z or the omega. Right? They're two different things. And they'll give us some condition for either the z or the omega. And this is you're probably looking at this and going, what on earth is he talking about? Because it just doesn't make sense with what I'm doing here. But don't worry, once we look at examples, hopefully it'll clear it up a bit. But there's certain things to look for. But the idea really is, whatever condition they give us, we want to make that the subject. And then that'll get us on our way of finding the locus. Things we look for. If the condition they tell us is omega is purely real, and we've seen some of these sorts of ideas there, then we know, oh, okay, they're telling me that the imaginary part is equal to 0. That's useful for working out an algebraic solution. For your geometric solution, what it's telling me is the argument is either 0 or pi, because all real numbers lie on the horizontal axis. So we know its argument is either 0 or pi. And the imaginary equivalent one would be, for algebra, if we're going to take an algebraic approach, the real part would be equal to 0. And geometrically, well, okay, now I know it's on that the y-axis. So the argument must be plus or minus 90 degrees, or plus or minus pi on 2. Then there's this other sort of thing. For years I had to come up with a way, how do I describe this? So this is how I do it. You see arguments, and then inside the argument you've got like a fraction, and on the top there's a linear function, on the bottom there's a linear function, and it's equal to some angle. So that sort of thing, again, when we look at an example, you'll see what I mean. Then I know that that locus will turn out to be an arc of a circle. And when we look at our example, I'll show you why. It'll turn out to be a minor arc if this angle is bigger than 90 degrees. It'll be a major arc if it's less than 90 degrees. And of course, if it's equal to 90 degrees, it's a semicircle. So let's look at some examples. Find the locus of W if W is z plus 2 on 2. And the condition we've got is the modulus of z is equal to 4. So what is this question actually saying? What you have to imagine is two Argand diagrams, because unfortunately in our world we can't work with 4 dimensions. And we need 4 dimensions to do this. Because normally when we're just using real numbers and we say y is a function of x and we can draw a nice picture, we only need 2 dimensions to do that because we've got 2 variables. But now I've got 4 variables because w is going to have a real and imaginary part, so there's 2 variables there. And z has got 2 variables, real and imaginary part. So I've got 4 variables. And obviously we can't plot that in anything that we can physically see in our world. So you have to imagine there's 2 Argand diagrams. And so there's one Argand diagram, I guess, for the input, and there's one Argand diagram for the output. And so the input of this is z plus 2 on 2, but the input is actually z, of course. Z is what we're putting in. So on our input diagram, we want to substitute in every complex number such that its modulus is 4. So the input would just be a circle radius 4. And we're going to plot that. And so the question is, what does the output look like? If I was to grab every single complex number on that circle, substitute it into this little formula, what will we get out? That's what it's basically asking. Okay, so the idea is the formula that they give me, whatever the condition we know, which in this case is the modulus of z is equal to 4. So I'm going to try and make z the subject. So that's how I'm going to start. So I've got w equals z plus 2 on z. I want to make z the subject. So zw is z plus 2. So that factorises to be zw minus 1 is equal to 2. Rearranging that, there's our answer. Z is equal to 2 on w minus 1. Now I can apply the condition to see what the locus looks like on the other one. Because I've now got z the subject, well, I know the modulus of z is 4. I can now work out what's happening with w, because I can say, well, that now means that the modulus of 2 on w minus 1 must be equal to 4. So the question is, what does this look like? Play around with it a bit. I'll turn... all I did in the first line was find the absolute value of 2. It was very tricky. Turned out to be 2. Okay. Then I've turned it upside down, but that and also fixed the other side. So we end up with w minus 1 is equal to a half. Because when I turn upside down, I get w minus 1 on 2 is equal to a quarter. Multiply both sides by 2. Now that's something I recognise. That's a circle. Centre at 1, radius a half. So I now know that on my new diagram, on my output diagram, I'd end up with a circle, centre at 1, radius a half. So it's x minus 1 squared plus y squared is equal to a quarter. Right? So as I say, we really need 4 dimensions to plot the whole problem in one thing. Obviously, we don't have 4 dimensions, so we think of it as 2 Argand diagrams, one for the W's, one for the Z's. Okay, so this time we're going to find the locus of Z. The formula, or the function, is W equals Z plus 1 on Z minus 1, and this time the condition is W is purely real. So this time I know the output. All the answers will be on the real axis. Question is, what's the story with the input? Going to make Z the subject, but not quite sure. So I'm going to go back to algebra for this one, because the condition is on W. So it's purely real. And remember, we said if it's purely real, the imaginary part was going to equal 0. So that's why I've broken it up into real and imaginary. So Z plus 1 would become x plus 1 plus iy, over z minus 1, x minus 1 plus iy. Realising that, so multiplying by the conjugate, I get this wonderful expression. I don't need to waste a lot of time expanding the whole thing out, because remember, we're only concerned with the imaginary part. Remember, we want the imaginary part to equal 0. So if the imaginary part is equal to 0, just grabbing the imaginary parts, on the top of the fraction I've got minus x plus 1 times y, plus x minus 1 times y. Also, I don't have to worry about the bottom of the fraction, because if a fraction equals 0, got to be the top of the fraction equals 0. So now I just have to play with this. Let's see what we get. Okay. Oh, y equals 0. So this is, well, some might say it's rather boring, because if you think about it, it's saying y equals 0. Well, what's that line? The x-axis. So this particular function, it gets numbers that are purely real, substitutes them in, and get answers that are purely real. But mind you, not necessarily the same number. However, and here's the bit you've got to look at, it will not include the point 1, 0. So we don't actually have the whole axis. Because if you go back to the original question, we know we can't have 0 on the bottom of the fraction. So therefore, we could never have substituted in z equals 1. So we have to exclude that from our input, our locus of what we're putting into this. So excluding 1, 0. That's how I would do it algebraically. Geometrically, much more fun, and I personally think a lot quicker. So if w is purely real, then I know the argument of w will either be 0 or pi. The argument of z plus 1 on z minus 1 is either 0 or pi. Now, remember in that list of things I said, things we look for? There was one that said argument of, and if you've got a fraction, linear function on linear function. That's what I've got here. I know I'm going to end up with an arc of a circle. Problem is here, the angle is 0 or pi. So I actually don't end up. If it's 0 or pi, I end up with a straight line rather than an arc of a circle. Because this is what happens. If you split up the argument of z plus 1 minus the argument of z minus 1 is either 0 or pi. So we're saying the difference in the arguments are nothing, so they have the same arguments, or there's 180 degrees between the difference. So I'm joining up z, the vector that joins up to -1, and I've got a vector that joins up to +1. I've got to draw. See, if I put it here, then the arguments, that's a case when it's in the middle where they differ by 180 degrees. Whereas if I put it, say, on the outside, then that vector would go that way. That vector would also go that way. Those arguments would be the same. So 0 or pi, they have to end up being a straight line. So, but not including those points. So I've ended up with a different exclusion. Well, hang on, that's a problem. So I've got to go back to the original question and ask, what did the question have? The question was, z plus 1 on z minus 1 is purely real. I changed that question. I changed that question to be the argument of z plus 1 on z minus 1. And remember, just like when we're solving equations with normal algebra, sometimes when you change the question, you create extra solutions. And that's what I've done here. I've created an extra point of exclusion. Okay? So you go back to the original question, and no, actually it is possible to put in -1. Because if I put in -1, I'll get 0 on -2, which is 0, and we consider 0 to be a real number. So it does work. So always go back to the original question to check those exclusions. All right, here's one where it doesn't equal 0 pi. This will be an arc of a circle. And I'll show it to you by the same way. If I split this argument up, I'll get the argument of z minus the argument of z minus 4 is pi on 6. So again, I'll get z, I'm going to join it up to, 0, and I'm also going to join it up to 4. The difference in the arguments will be pi on 6, which is, of course, how many degrees? 30 degrees, that's right. Okay. So, again, I'll just place z randomly. If I join it up to 0, and I join it up to, what was my other point? 4. We're saying, I'll call that one alpha, I'll call that one beta there. We're saying the difference between those angles is pi and 6, 30 degrees. Well, that's certainly possible. Okay. Now, which one's bigger, alpha or beta? Alpha has to be. All right? It wasn't a trick question, because alpha is the exterior angle of a triangle, and the exterior angle would equal the sum of the two interior, so it would be beta plus something. So alpha has to be bigger. Now, alpha represents the argument of z minus 4. So how on earth could I get beta, if you like, subtract alpha, and get a positive number? How is this possible? Any ideas? Say it again. Yeah, if it was below, because then we're talking about negative angles. And so if z was underneath, now alpha is still bigger than beta, but it's a negative. And so I've got negative acute angle minus an obtuse angle, it will become a positive number. And so that's how I tell whether z is above or below, by looking at which one is minus which one. So drawing the diagram is very handy for this, so you can work out where it is. All right, so let's look at that. There's my Argand diagram. So join one up. As I said, I've just joined it down because we now know z's below. And there's 4. We'll join that up. Okay? All right? And that's what we worked out. We said argument of z was greater than the argument of z minus 4, so it must be below the axis. And when I say greater than, I'm talking about the magnitude. I'm not worried about the minus or the plus. Okay. I found the midpoint. Has anyone worked out yet why this turns out to be the arc of a circle? That angle, you'll notice I've labelled pi and 6. Because I said the difference between these angles are pi and 6. Let's call that one theta. So we're saying alpha minus beta is theta. But our theta is pi on 6. Okay. Again, exterior angle of a triangle. Let me write it a different way and you might see it more obviously. Okay. Alpha will equal beta plus pi on 6. Okay. If I rearrange that, I get alpha minus beta is pi on 6. So that's why it turns out to be the angle between. Now, you were saying something? Exactly. Angles in the same segment are equal. So it doesn't matter where Z is, this is always pi on 6. And that's why we end up with an arc of a circle. It also means then that the line joining 0 and 4, the 2 points, turns out to be the chord that arc sits on. So I now know that's a chord. That's why I found the midpoint. Because perpendiculars from the centre will bisect the chord. So I'm going to draw a perpendicular. I know the centre of the circle must be below, and it will have an x-coordinate of 2. I just need to work out the y-coordinate now. How to work out the y-coordinate? That will be our radius of our circle, the hypotenuse of that right-angled triangle. Because if that's now the centre, and we said that was a chord, so it's on the circumference. So I can work out the radius. That angle in there will be 30 degrees. The angle at the centre is twice the angle at the circumference. The angle at the circumference is 30 degrees. Therefore, the angle at the centre is 60 degrees. But I've chopped it in half, so it's back to 30 degrees for that right-angled triangle. So using that right-angled triangle, I can do a bit of trig. Y on 2 will be the tan of 60 degrees. So I now know y is 2 root 3, but it's below the axis. So the centre is the point 2, negative 2 root 3. The radius we can now work out to be 4. So, a lovely final statement. The locus is the major arc of the circle, x minus 2 squared plus y plus 2 root 3 squared is equal to 16, formed by the chord joining 0, 0 and 4, 0, but not including these points. We exclude the endpoints because if you go back to the original question, if I substitute in 0, I would have the argument of 0. You can't have the argument of 0. We haven't started yet, so we don't know where we're going off to. So 0 doesn't have an argument, so it doesn't work. If I substitute in 4, then I've got 0 on the bottom of the fraction. And we can't have 0 on the bottom of the fraction. So both endpoints of this chord end up being excluded in the locus. Probably one of my more favourite locus questions that we can get. Probably one of the more involved ones as well. So here's a handful of ones. Grab some from Patel, just 2 from Patel. There's the Cambridge exercise, but then I also printed off a sheet of past HSC locus questions so you can see the sorts of things they ask in the HSC.